So, Bismillahir Rahmanir Rahim. Today we will talk about a new concept which is torque. If we apply a force on an object, for example, this is a force, and if we apply a force on an object which has a mass m, according to the Newton's second law, it will accelerate in this direction. So the force will the force will try to move this object in a straight path. But today we will talk about the torque. Torque is a turning effect of a force. So the torque, is a turning effect of a force. So what does that mean? For example, we take an example of a door. So we have here a wall. So this is a wall, and we have a door which is attached to this wall. So this is a wall, and then we have here this is a wall, and then we have a door which is attached to this wall. So if we apply a force, so we take 3 points. For example, we have A, and here we have B, and here we have C. What will happen if we apply a force here? So this is a force A. This is if we apply a force here. So this is a force B, and then we apply a force here. So what will happen, or what's the difference between these 3 points? So if we apply a force here, we will be able to move. It will be easier to move or to push this door if we apply a force here. So this distance here is RA, and here from this distance we have RB, and here the distance is 0. So if we apply a force at the distance RA, so here it will be easier to open or close the door, or it's easier to move or to push this door. But if we apply a force here, it will be a little bit difficult compared to this point. It will be a little bit difficult to move or to push this door. Similarly, if we apply a force here, it will be almost impossible to push a door. So the torque here mathematically is F force dot R, or cross R. So what does that mean? This means that if the force is large, if we apply a large amount of force, the torque, the turning effect will be large. If the R is large, so for example here we saw when the R was big, here it was easier to move, so the torque, the turning effect was more here. Similarly, if we apply a force here, so which is the RB is smaller here, so it was difficult to move. So this equation here, it makes sense. So we take the example, same example of the door here. So we have a door, and we apply a force here, but the angle here is 90 degrees. So if the angle is 90 degrees, that means that the torque is simply F cross R, which is a vector. So the torque will also has a direction here. So this will have a direction. We will talk about the direction. We can find the direction with the right-handed rule because it's a cross product here. But what will happen? So this is easy, because if we have so this is the moment arm. So this distance, the R, is called the moment arm. So if there is the angle between the moment arm and the force is 90 degrees, which means the cross product means, so F dot, so the cross product we can also write F magnitude of f, magnitude of r, sine of theta, and direction. So sine of 90 is 1, so the torque will be maximum here. But right now we will discuss if the angle here is not 90 degrees. So we will discuss now the case when the angle is not 90 degrees. So we have the same door here. So the force here, so this is the force. So this is the force and it's making an angle here. So here we have the L, and L is the distance between the axis of rotation. So the axis of rotation means the point which will be not moving and the door will be moving. So this is the axis of rotation, and the L here is the distance between the axis of rotation and the point where the force is acting, and the force itself is making an angle. So we extend the line of action of force to the other side, and we will make a triangle to just simplify this problem. And then using this triangle we can use the trigonometric ratios. Extend this line of action of the force. So this is the line of action of force, and we have to make line here. So this is now 90 degrees. So, and here is actually the moment arm right now, and this is L. So if this is theta, so this should also be theta here. Right now what we see here, we see a triangle, a right angle triangle. If we have, because we have here, you can see here we have a perpendicular here, we have hypotenuse here, so this side is the hypotenuse and this side is the base. So right now, just for simplicity, I will make the same triangle here. So we have here, so this is the 90 degrees, so this is the same angle here. So this is 90 degrees, so this should be hypotenuse. We have angle here, so this is the angle. So the side which is in front of the angle is perpendicular, and this side is base. So right now this is the R here, so we can also see here, so this is the R and this is the L. We just simplified the same thing here. So right now we want to know, so here the R here, so because in the torque we have the here R F cross R, so we want to know what's the R is here. So R is sine of the L sine of theta. If we use the trigonometric ratios that we discussed in our last lecture, if we go to the last lecture, so we have discussed this right angle triangle, and then sine theta, if we use that sine theta, so we will have the same relation here. So right now, so we have the R, so we have the F R sine of theta, so it will also has a unit here, direction here. So this direction here you can see here in this case, so for the cross product, so we discussed in our previous lecture for the direction of the cross product, we use a right hand rule. So right hand rule means if you use a right hand and we try to rotate this, the force, the first thing here, so which is the first is force, and we try to rotate this towards the second vector, which is r here, along the smallest possible angle, and this our thumb will be representing the direction here. So in this case, if we apply force here in this direction, the direction will be out of board, which is represented by a dot here. So this is the direction. So this is the one way of finding this torque here when we have the angle here. So the second way, so we take the same force here. The force here we can see here there is an angle. So we take the same force. So we take the same force. So this is the force, and we split this force into two perpendicular components. So that also we discussed in our previous lecture. So here, this is the Fy, this is the Fx. Right now, what we see here, if we take this, the door here, the example of the door here, if we apply a force, so force is in this direction, so force here is in this direction, so this theta, the angle is known here. So the door is moving in this direction. So the force that is active force or the effective force, that is Fy. Since there is no motion here in the x direction, so this Fx plays no role here. So we can just ignore this Fx. So in the previous lecture we also found the magnitude of the Fx and Fy. So the magnitude of Fx was F cos of theta. But here this force, because in our case, in the case of torque here, so this horizontal component of the force is inactive, it plays no role here. So what we do, so for our purpose we use the Fy, which is F sine of theta. So F sine of theta, so now we have the Fy here, so that we know what is the effective force and we know what is the distance between the axis of rotation. So this is the axis of rotation and the point where the force is actually acted. The effective force here is the Fy. So here this force, so this is the Fy, and this distance is known. So we can simply write the torque equals force, the moment arm, sine of theta, and here is the direction. And the direction we can find out using the right-handed rule. So now since we derived the formula for torque, so which is F dot R sine of theta, and this is the direction of the force. Now we take an example. So the example is, if a mechanic tightens the nut of the bicycle using the 15 centimeter long spanner by exerting a force of 200 newtons, find the torque. So there is for example here a nut, and then we have a spanner. So this is a spanner. So here is the line of action of force, because we want to tighten this nut. So the force is applied, the force is 200 newtons, and the distance here is 15 centimeter. So since here we know the angle is 90, so the force we know is 200 newtons, the L is 15 centimeter or 0.15 meter, and the theta is 90. So this is the length here. So we know that the torque is equal to the force cross L. So this is a vector, this is a vector. So force theta. So since the angle is 90 degrees here, so the sine of 90 is 1. So the torque is 200 newtons multiplied by 0.15 meter, which is the torque here is 30 Newton meter. So the unit of the torque is Newton meter. So we can see here we have the force multiplied by the length. So the unit of the force is Newton, and the unit of the length is meter. So the unit of the torque is Newton meter. So now we take a second example in which the two forces are applied in two different directions. So we have another example. So the example is, so we take the example of a door. So this is a door. This is attached to a wall. So this is the axis of rotation, and there is one force which is applied here is F1, so which is 200 Newton, and the distance between the axis of rotation and the line of action of force, which is here the moment arm, this is 3 meters, and we just consider for simplicity the angle 90. So the sine of 90 will be 1. And there is another force which is applied at the middle of this door, which is 400 Newton. And this distance, and this is in the middle of the, so this is the F2. So and this distance is R2 equals 1.5 meters, and this is R1. So first we find out how much is the torque, because of how much torque is produced because of this F1 force, which is 200 newtons, and then we will find out what is the torque that is produced with the 400 Newton force which is applied here, and then we will find out what is the net torque on this whole system on this door. So the torque, because of the torque 1, because of this force 1, is equal to F dot R, and sine theta we just ignore because sine of 90 is 1. So here we just take the 200 here, 200 multiplied by 3, so tau 1 is, we take 6 plus 600 Newton meter. So plus means here it's out of the board the direction, it's representing the direction. Since the other force is in opposite direction, we will take the opposite direction here. So tau 2 is 202 multiplied by R2 equals, so this force here is 400 newtons multiplied by 1.5 meter. So the tau 2 is minus 600. newtons meter. So here you can see here, so if we use the right hand rule, because of this force, since this force is in this direction, so here is the torque produced is outward here, and the other force is in this direction, so this is inward. So the direction one is in this direction out of the boat, and the second one is in towards the or inward here. So this is plus 600 Newton meter, and this one is minus 600 Newton meters. So the net torque is equal to, so this one, so torque 1 plus torque 2 equals plus 600 Newton minus 600 newtons, which is equal to 0. So the net torque here is 0, which means that the door will be in equilibrium, nothing will happen to the door. So this is one of the examples. In this lecture we will also discuss about the equilibrium. So this is one of the conditions for the equilibrium, that the net torque is 0. Although you can see here we have a 200 Newton force is applied here, and then we have the 400 Newton force is applied, but since the net torque is 0, nothing will happen to this door. Since we talked about torque, so right now we take another example. So we have here a seesaw. So this is a seesaw which is balanced on this pole here. So there is one person who is sitting here, and there is another person who is sitting here. So this is the axis of rotation here in this case. So due to the gravity, so there is a force which is m1g, and we have a force which is m2g, or we can say weight of this object, and here this is also the weight of this object, which is also in this direction. So this force is trying to move this seesaw in this direction, which means the clockwise. So here is the because of this force, the seesaw is trying to move in a clockwise direction, and here due to this force, this gravitational force, the seesaw is trying to move in this direction. And here this distance is L1, and here this distance is L2. So when we want to balance this the system, the seesaw here, the clockwise torque must be equal to the anti-clockwise torque. So in this case the system will be balanced. So this is the anti-clockwise torque, and this is the clockwise torque. So we can also write the torque, which is the force. So here is the force, so this is force, and L1, and L1 is the moment arm here. So this must be equal to the weight of this this object here. So this here will be a balanced system, or we can also say that this system will be in equilibrium if the clockwise torque and the anti-clockwise torque are equal. So to give you some feelings, so we will take an example. So here we have a hanging object here, so which is M1, and we have here another object which is M2. So again, because of the gravitational force, there will be gravity M1g, which will be equivalent to the weight, and because of gravity we will have M2g, which will be equivalent to the weight of this object. So the distance from here to here is L1, and distance from here to here, or the moment arm, is L2. Right now, so the L2, so the weight here is known, which is 10 newtons. So 10 newtons. So this is the system. So we want to know what's the, so this is 1. So we want to know what is this weight. So this is given and these two distances are given. So we want to know what is the weight of this object here. So this is not known. So we have and then we will have the distance L1 here is 0.25, and this is meters. So we have the L2, which is 0.4 meter. So what we see here, that the L2 is larger than L1 here. So so if we put these values here, so we will get, so this is also 2, so this will come here. So the W1, if we put these values, so we will get 16 newtons. So what we see here, the weight of W1 here, so the weight of the object 1 is larger than weight of the mass 2. The reason is because the distance here, this distance is smaller. To balance this, this distance is smaller than this one. To balance the system, so the W1 must be larger than W2.